Okay, good afternoon. Assalamualaikum. I wanted to highlight to you from our previous class on the pinch design method. Okay, if you still remember for the below pinch analysis. Yeah. Okay, below pinch. For the below pinch, last time we had discussed that stream 2 and stream 1 is not feasible. Stream 2 and stream 1 is not feasible because of CPH not meeting the larger than CPC. Okay, this one is pinch, below pinch. So stream 2, stream 1 is not feasible due to the CPH lesser than CPC. Okay, only stream 4 to stream 1 meet the requirement. Okay, but at our final design, for the below pinch, it has a stream 2 transferred to stream 1. Okay. Okay, last time I said, let me check. So I have gone through the textbook. There is one note at one note. Let me share with you. This is a good book. This is the notes is extracted from this book. Okay, the notes is extracted from this book, Robin Smith. So here it mentioned okay, this part. This part, focus on this part. The note over there. The CP inequalities given by the equations. Okay, this equation is the requirement. The CPH larger than CPC for below pinch. CPH smaller than CPC for above pinch. Okay, so there's a note down there. Those requirements only apply at the pinch. Okay, only apply at the pinch. And when both ends of the match are at pinch condition. Both ends of the match are at pinch condition. Meaning that from our lecture note, from the case here, first we had exchanged stream 4 to stream 1, 17.5. Okay, then stream 1, the temperature changed from 20 to 52. Okay, the temperature change. Once stream 4 exchange to stream 1, the temperature change. So it is not at pinch anymore, stream 1. Okay, that's why stream 2 can be transferred to stream 1. Okay, when stream 4 exchange heat 17.5, temperature on stream 1 had already changed. So that's why stream 2 can transfer to stream 1 according to the note just now. CP inequalities only apply at the pinch. Okay, and when both ends of the match are at pinch condition. Okay, that explains why at the end, stream 2 transfer to stream 1. Okay, this one not in your notes. Just put in this in your notes, lecture slide. This. Okay, so this statement explains the exchange from stream 2 to stream 1. Okay. Okay, that's for chapter 4 last time. Now I proceed to chapter 5.
The first broke, so we had to put it. So since the first broke, so I had to quickly go change the circle.
Okay, so now I proceed to chapter 5, chemical process optimization. Now the general definition of optimization is you need to find the best solutions to the problems. Okay, best solution. It is the art of determining the best solutions. How to find the best solutions? To identify what is your purpose. Okay, purpose of the optimization. And then what is the value of the function? The objective function is subject to a number of restrictions. Okay, so for optimization, you need to at first identify what you want to maximize or minimize, your aim, your purpose. Okay, maximize or minimize. Then what is the value of a function? We call that as objective function. Okay, objective function means what affect your aim. For example, the parameters. Okay, let's say for example, the purpose, you want to maximize the yield of palm oil. So the function, yield of the palm oil. What are the parameters affecting the yield of palm oil? And then number of constraints, number of restrictions, called as constraint. So constraint, perhaps you want to minimize the cost, or the yield should be at certain concentration. That is your constraint. Okay, for example, as I mentioned just now, for example, let's say you want to your purpose maximize palm oil production. Palm oil yield. Okay, this is your purpose. Maximize. Maximize palm oil yield with minimum cost. Okay, so your purpose is to maximize the yield. Objective function, your yield. What are the parameters affecting your yield? Perhaps the temperature, the pressure, the loading. Okay, and then your constraint will be the minimum cost. This is your constraint. This is the function. Okay, another example to minimize the COD content in wastewater treatment to meet the DOE requirement. Okay, so your purpose is to minimize the COD. Objective function, your COD. How to minimize it? Constraint the DOE requirement. Up to what concentration? That is your constraint. Okay, so optimization, it affects on the financial and also the plant performance. Okay, for the plant performance, it can improve the yield of valuable products, reduce the energy consumption, okay, and higher processing rates, perhaps longer time between shutdowns, okay, and reduce maintenance costs. Can be either of these. Okay, this is another more example. So, for example, your purpose is to maximize the reactor conversion. Okay, purpose, your aim lah, your purpose. Then subject to reactor modeling equation. This is your objective function. Okay, with the constraint limitation on the T, P, and X. X perhaps here is the concentration. Okay, so you must identify what is your purpose. And then what affecting that purpose. Okay, with is there any constraint to meet? Okay. Now, optimization of a distillation at design stage. Okay, for example, here we have the relationship between the number of stages and also the reflux ratio. Okay, both of these, number of stages and reflux ratio, it is linked to the capital cost and also the operating cost. Okay, the more stages, the higher the capital cost and the lower operating costs. Okay, how do you think? Higher, more stages, higher capital costs, but lower the operating costs. Operating costs here, perhaps the utility costs. How can you have higher capital costs but lower operating costs? How does it affect? How it affect? How they correlate? Mm-hmm. Mm-hmm.
the higher efficiency investment is high, but if you go for payment periods, we can get profitable if we choose the lower governments.
How it relates?
Utility needs and then operating and maintenance costs.
Mm-hmm.
It's involved with chemicals, then cost as well.
Mm-hmm. Others? Yes, in long term, it will affect on your operating and maintenance costs. So how about others? What do you think? How it relates? The more stages, high capital cost, low utilities. Any idea? Mm-hmm.
Higher and for picture costs to build high quality.
Capital cost, yes. How about the operating cost in terms of the utility? Okay, we look for the utility only. Reduce heat duty. Reduce heat duty of the reboiler and condenser. Correct? Yes. Make sense? So when you have more stages, you can reduce the reflux ratio. Then it affects on your condenser and reboiler duty as well. Okay, when you have another thing, when you have more stages, let's say your aim is to get 95% purity. So instead of having a few distillation columns to achieve that high purity, you increase the number of stages. So having, for example, having one distillation column with, for example, let's say having one distillation column with, let's say, 10 stages. Okay, instead of having two distillation column with 5 stages each. So if you have two distillation column, capital cost is higher, operating cost also is higher compared to having one DC with 10 stages to achieve that 95% purity. Okay, for one column of 10 stages, capital cost is high because you increase the stages, okay, to install all the stages, but then you have the high purity, then you reduce in terms of the operating costs. If you have two DC, then you have two operating costs for two distillation column. Okay. So that's how it relates number of stages, reflux ratio, capital cost, and operating cost. Okay, so that's why you need to determine which solution meet your requirement. Okay, so from here, you can minimize the total cost while meeting the spec. You aim to achieve 95% of purity. So having one DC with a higher number of stages can achieve the 95%. Meanwhile, having two DC with 5 stages also can achieve 95%, but then the cost will be different. Yes? Okay. Okay, now we go to the definition of the terminology. You need to understand the definition of the term first. Okay, because from the given problem later on, you will need to identify what is your objective function, what is your decision variables, and what is your constraint. Okay, so objective function that you wish to minimize or maximize. Usually economic value. Okay, for example, the profit, the production rate, the energy, the cost. Okay, that is your objective function. The decision variables is the variables that you can manipulate in order to minimize or maximize the objective function. Okay, let's say you want to maximize the production rate, maximize production rate. So what are the variables that you can manipulate? Okay, for example, you have the flow rates, perhaps the concentration, temperature, pressure. Okay, integers here means number of trays. Then binary, select or not to select. Okay, so these are the decision variables. Constraint is the limitation. It can be physical, economic, or policy, or environmental related. Okay, for example, just now to reduce the COD concentration in the wastewater to fulfill the environmental regulation. So that is your constraint, environmental regulation, the regulation. Okay, or perhaps your constraint let's say your aim is to maximize the concentration of your product by 95%. So constraint here is the concentration, 95%. Okay. And, so these are the terms. Now we go to the features. Objective function. So you later on, you need to identify the function. Okay, the function as in fx. Okay, you will need to come up with the equation that relates to your problem. X here is the decision variables. Perhaps your flow rate, perhaps range of flow rate. Okay, there are a range of it. Subject to C, the constraint. Okay, here equal means equality constraint. Inequality constraint. Okay, this sign represents the inequality. This sign represents equality. Okay. Now, as overall, this is your function. Fx. Inside here, the x here is your decision variables. So here it is in the range from x1 to xn. Okay, this is your decision variables. Inequality constraint when you don't have the equal symbol. Okay, here not necessary equals to 0. It depends to your constraint. Okay, later we'll go one by one for the example. We just need to understand the term first now. Okay, so these are the candidates for the measure objective function, where X is a design variables that approximate profitability measures. Okay, so these can be the decision variables. Now this is the yeah. Let me enlarge a bit. Okay, here is this is the objective function. Okay, your function. Then this is your constraint. Perhaps subject to the constraint X larger than 30, or it can be constraint equal to 30. Okay, it's up to you how to decide what is your constraint. Okay, we go example later on. Now, constraint. To identify the constraint. For example, in process simulators, most of the equality constraint equals to 0. Okay, are the model equations relating to the mass and energy balance. Okay, some inequality constraints simply place lower and upper bounds. You must have a range. Sometimes the constraint is in between the range. Okay, for example here, 95% recovery of species I in the distillate. Okay, so this is the function. You want to identify for inequality more or less than the 95% recovery. Inequality must be larger than 0 or lesser than 0. This is the constraint. Okay, for example, we have here F is 10 kg per second. Species I. Let's say I is ethanol. Okay, our target is 95% recovery of the I in the distillate flow. Okay, so we come out with this equation. XID minus this one. Okay, so you will get equals to 0.95 ZIF. Okay, the distillate here is our target, 95%. Okay, you should generate the equation. This one will not be given. You should know how to generate that equation. Okay, from the aim, 95% of the distillate is species I, the ethanol. Okay, with the constraint, more or less. So more or less. Okay. Now later we go one by one on the example. Okay, classification of optimization problem. There are 5 optimization problem. classification. Okay, the types. We have linear programming, the LP, where the mathematical program is linear. Okay, that's why it's called linear. LP, linear program. Another one is non-linear. Okay, number 3 is integer. Okay, non-linear, it can be power 2, quadratic. Okay, non-linear. Integer program, all variables must be assumed as integer values. Okay, the most common 0 and 1, the binary integer variables. Okay, number 4 is the mixed integer linear programs. Mix of linear and integer. Some linear, some are integer. Number 5 is the mixed integer non-linear programs. Non-linear and integers. Okay, we go for linear programming first. Linear program model. Linear means power 1 only. Linear. Okay, x power 1. Linear. Now, example 1. A farmer is preparing to plant a crop in the spring and needs to fertilize a field. Okay, there are 2 brands of fertilizer to choose from, Supergrow and Crop Quick. Each brand yields a specific amount of nitrogen and phosphate per bag. Okay, the focus is on nitrogen and phosphate. Supergrow has 2 nitrogen and 4 phosphate. Crop Quick, this amount. Okay. Now the farmer requires at least 16 pounds. So equal or unequal? At least. At least. So if at least means it can be more or less. More. Right? It can be more. The minimum is 16. It can be 17, 18 at least. So this one is inequality constraint. Inequality. Okay, at least. Okay, the farmers requires at least 16 pounds of nitrogen and 24 pounds of phosphate. Supergrow costs $6 per bag. Crop Quick, $3 per bag. Okay, the farmer wants to know how many bags of each brand to be purchased in order to minimize the total cost. Okay, minimize the total cost. So your objective function is what? Objective function. Cost, minimize the cost, total cost. Okay, we go step by step. So just now your objective function is to minimize the cost. Now minimize the cost. How it get this equation? Minimize cost. Huh? Okay, so we look at the cost. Supergrow, $6 per bag. Crop Quick, $3 per bag. Sorry. Okay, so the X1 here refers to Supergrow. Okay, X1 is Supergrow, $6 per bag. Crop Quick, $3 per bag. So that's how it results in this equation. Okay, from the cost, we take that. Okay, the objective function. Okay, up to there, understand how it get the equation. This one, we take the cost because the objective function is to minimize the cost. Okay. Now, define the constraint. Equality constraint, we don't have equality. We have inequality. Because just now, the form it mentioned at least 16 of nitrogen and 24 of phosphate. Okay, how do this equation comes? Nitrogen. We focus on the nitrogen. Wait, I copy this one. Okay, the nitrogen. From this table, nitrogen per bag. Super grow just now is X1. Crop quick is X2. Okay, so we develop the equation for nitrogen. 2x1 plus 4x2 must be at least 16. Okay, then phosphate 4 super grow 4x1 plus 3x2 at least 24 equal or larger. Okay, that's how it get this constraint equation. Any question up to here? Okay, take your time first to understand how this equation works. The non-negativity constraint here is to indicate that negative bags is not possible. Negative bags of fertilizer cannot be purchased. Okay, not possible. So here, the sign would be equal or larger than 0. Means the X cannot be negative. Okay? Can? Okay? Then we apply the suitable optimization technique. Plot X2 versus X1. Okay, X2 versus X1. X2 just now is the crop quick. X1 is the super grow. Okay, just now we had the equation. This is for phosphate. This one is for nitrogen. Okay, so we plot, we find the point. For P, look at the P first. For P, when x1 equals to 0, P here. Okay, when x1 equals to 0. Okay, so when here 0, so x2 equals to 8. Okay, so that's how you get this point. When x1 0, you need 8 bags of crop quick to fulfill the 24 requirement of the phosphate. Okay, so if x2 equals to 0, okay, x2 equals to 0, so x1 would be 6. Okay, we focus on the phosphate first. If x2, let's say x2 equals to 0, so x1 equals to 6. So that's how you get the point here. Hmm. Okay, now we move for nitrogen. If x1 equals to 0, so x2 x2 4. Okay, so that's how you get the 4 over here. When x2 equals to 0, then you get 8. Now from the line here, the both of the two lines, it cross at this point, which brings this one is 5 of x2 to x1. This one. X1 is 5, x2 is 2. Okay, so here we have 3 points that we can consider. One, this is the first point, second point, third point. Okay, so using the x1 and x2 value, you plug into the objective function to find the minimum cost. First, we need to find how many bags that fulfill the constraint phosphate must be at least 24. Nitrogen must be at least 16. Okay, find how many bags that can supply at least that amount. To find how many bags, we use this equation. Okay, so from this equation, we identify few options. Once you have your options, plug in into this equation, the objective function equation. Okay, so now, let's say we take the first one. X1 is 0 plus 3. X2 is 8. So you get 24. That's how you get this $24. Okay, from the consideration here is the 3 points. Okay, but from the graph, if you notice, we have other points as well. Right. This one. 4 and this one. Yes. Different color. Here, the 4 and the 6. Now, why this one is not considered for the minimum cost? The 0.4 over here and the 6. Okay, another point here is x2 4. X1 equals to 0. X2 equals to 4. X1 equals to 6. X2 equals to 0. Okay, why we don't consider these points for the costing analysis? What do you think? What do you think, Avinash? No idea. Because it doesn't meet the constraint. Right, Frank? How do you think it doesn't meet? Correct. Okay, if you substitute back this value to the constraint equation, you will not fulfill the constraint. Okay, for example, this point, the first point over here, x0, x2, 4. So we put in the phosphate constraint equation. 4, 0 plus 3, 4 equals to this one, equals to 12, right? 12. This is for phosphate. But our constraint must be at least 24. So 12 lesser than 24. So it doesn't meet the constraint. That's why this point is not included, excluded. Okay, similar to this point. X1 equals to 6, X2 equals to 0. Okay, let's say we put in a nitrogen constraint equation. X1, 2, 6 plus 4, 0. So you get 12 as well. Where, which you need at least 16. So lesser than 16. That's why this point is not included. Okay, take your time to digest first. I walk around. You can ask questions if you don't understand. In this case, you must meet both phosphate and nitrogen. It is an N, not 4. According to your objective, please follow this to outline which we do. You have to compare like this. Because your objective function is to find the mean. So in learning is Okay, again I repeat, the point, this point and this point not considered because it doesn't meet the constraint. Okay, when you put into the equation both, it doesn't meet the constraint. The statement earlier, it mentioned at least 16 pounds of nitrogen and 8N. So both must meet the constraint. All points must meet the constraint. Okay, so once you find the correct amount of x1 and x2, plug in into the equation of the objective function. The aim is to minimize the cost. So that's how you get the minimum number of the cost. Okay. Okay. Now we go to the next example. Ready mixes produces both interior and exterior paints. Okay, from two raw materials, M1 and M2. The table provides the data of the problem. M1 is the raw material. Tons of raw material per ton of exterior and interior. So M1, 6 ton in exterior paint, 4 ton in interior paint. Okay, and then the maximum daily available ton is 24 for M1. Maximum. So it cannot exceed this value. Maximum. So it's a range. Okay, inequality. Now, profit per ton for each type of paint, exterior and interior paint. This is the profit. Okay. Now, a market survey indicates that the daily demand for interior cannot exceed for exterior by more than 1 ton. Interior cannot exceed exterior by 1 ton. Okay, now also the maximum daily demand for interior is 2 tons. Okay, determine the optimum product mix. of interior and exterior that maximize the daily profit. Okay, so your objective function is what here? Daily profit, maximize daily profit. So your equation, objective function equation must relate with the profit. Okay, we go step by step. Step 1 here, define the decision variables. X1 represent the exterior, X2 represent the interior. Okay, wait, let me copy the table. Okay, objective function. Because our aim is to maximize the profit. Okay, so that's how this figure comes in. 5, the profit for exterior. 4, profit for interior. Okay, profit, so we look at the profit. Yeah, there are many numbers over here. You should know which numbers to take in for the objective function. Okay, now define the constraint. Define the constraint. Just now, it mentioned from the table. Okay, we take from the table. M1 constraint. Yeah, M1. Maximum daily is 24 only. Cannot exceed 24. Okay, M1. So X6, X1 plus 4, X2 must be lesser or equal to 24. You have a few constraints over here. Okay, this is X1, X2. Okay, M2 constraint. 1 plus 2x2 must be lesser than 6. Okay, this one from the table. Constraint for M1 and M2. Now, constraint from the statement mentioned. A market survey indicate that the daily demand for interior paint cannot exceed exterior paint by more than 1 ton. Okay, interior X2. X2 cannot exceed by X1 more than 1 ton. Okay, that's how you get this equation. The market limit. In exam, this constraint will not be provided. You need to generate on your own. The question just give statement like this. So you must generate your own. Okay, the last constraint will be the demand limit. Maximum daily demand for interior X2 is 2 ton. Maximum. So X2 cannot exceed 2. Up to here, any question? To identify the objective function and also the constraint. Can? Can? Okay. Simplification here is not applicable. Later, in the next example, you see what does it mean by simplification. In this example, not applicable. Okay. Now, step 5, choose the best suitable optimization technique. Now, we use graphical method. You can verify using solver. Tomorrow, if possible, bring your laptop so that we can try to do using solver. Okay, Excel. Now, from here, from all the constraints just now, we plot the graph. Okay, wait, I copy back the constraint. Yeah, so these are the constraints, the constraint equation. So we plot one by one. You must have 4 plots. Okay, M1 constraint. M1. So another square one, M1. Where when x2 equals to 0, so x1 equals to 4. Okay, x1 0, x2 equals to 6. You get that line. Okay, M2 constraint. This one. M2 constraint. Okay, when x1 equals to 0, x2 equals to 3. x2 0, x1 equals to 6. Okay, why we start at 0? Why start at 0? Why we choose at 0 for each axis? Why you choose 0? Huh? It cannot be negative, correct? You can start. Can you assume 1, either of the number? x1 equals to 1. Can. But we set as 0, we want to find the minimum of the other value. Okay. Now, market limit constraint using this equation. Market limit is the triangle one. Okay, so you get this. When x2 equals to 0, x1 equals to -1. x1 0, you get x2 equals to 1. Okay, the last constraint would be the demand limit. x2 must be lower than 2. 2 or lower, this one. Okay, 2 or lower. Okay, so meaning that your affected area is this part only. Because your X2 cannot exceed 2. It is the demand limit. Okay, your interior paint must be 2 or lower. Okay. Which one?
Last one.
Uh-huh.
We are taking from X2, that section, and then we go out the X, and then we can see in X1.
Oh, because the largest value at this axis is 6. Yeah, that's why it start over here, because the largest is at 6. Okay. So it works only on this area. Now your objective function is to find the maximum profit. This is the equation that you generated earlier. Now to find the maximum daily profit, in between this area, plug in the value into the equation over here. Then you find the maximum. Here it takes x1 equals to 3, x1, 3, x2, 1.5. Here, this point. The crossover, the cross here. This is the 21 point. Okay, you can try this point as well. 2, x2 is 2, x1 is 2 here. This one equals to 18. This point. Okay, so any point at the affected area, find the maximum profit. Okay. Now take your time to digest. I'll stop here first. Tomorrow we proceed with another 2 examples. Take your time to digest first. Mine is y is x, y axis is x1. Yours is y axis x2. That is the same now. Okay, so I stop here. For those who haven't capture your attendance, wait,